Hello, hey, howdy, hi. It's Robert Jordan from Cat Full of Ghost Electronics, and I've finished my club mate. The heater's on, the cat's here, slightly off screen, which means it's a perfect time to talk about the EMS Specter, or the Open Specter FPGA project that I am working on / started. The EMS Specter, this beautiful video synth here, is a bit of an oddity and a rarity. Oddity in that it's enormous, strange, dating from the late 70s, early 80s kind of period. It was a bit of a one-off direction that EMS, a company normally known for their synthesizers, went. But what is particularly interesting about it is that only 14 or so were believed to be made. And there's one in Australia, here in Melbourne, that MES has. It's currently not in a fully working order. This is a very old, very complex thing. So because there are not that many in the world, and because it's quite hard to find good sort of information and visuals from, we get a couple of photos, we've got a few videos. This video is from someone I know, which just goes to show you kind of how few videos there are. And here we've got some weird kind of chain stuff. So you can't really find that many videos on it and what it does. Because of its size and cost, very rare, but it has a very kind of historically important point in video synthesis. And so, because of all these things, I thought it'd be a very good idea to try to clone it. Try to make it so that people can actually get their hands on it. Use it and kind of explore what I think is exciting about both this synthesizer and this kind of time in history. As such, I've started Open Specter, which is designed to be an FPGA-based clone of this original beautiful machine. I'll have the link in the description, but here it goes through everything that is getting built, all the different parts, information if you'd like to contribute. At the moment, FPGA engineers are really what we're looking for, but in the future there will be opportunities for other types of people to get involved in terms of electrical circuit design and such. The way that this came about, I got quite lucky that a friend of mine, Remy, who was also working on the project from an industrial design and interface direction, had access to this, as well as a whole bunch of other great information about the particular EMS Spectre that's there. So, brilliant. Handwritten by the designer Richard Monkhouse himself. When I first came across this circuit, and I was kind of poring over it, trying to think about if I could do something with it, if it could become something, one of the first kind of things that I noticed was that a lot of it is digital logic. The majority of the system is digital logic. And for reference, it's all controlled with these big patch bays here. So this patch bay here lets you route all the digital signals together. This second patch bay lets you route all the analog signals. And then we've got faders for some dedicated stuff. And so what I realized pretty quickly looking at all of these schematics is that this machine was incredibly complex in the late 70s because in order to do even relatively simple things, like if I scroll back up to the top here, so we've got these things. We've got this X counter, X and Y counter. So in the EMS Spectre, the X counter counts every pixel, and then that clock signal is divided by 2, by 4, by 8, until it's been divided like that a total of 9 times. And then the same thing happens with the horizontal pixels, and I say pixels, but it's an analog video signal, so they're not exactly pixels, but for this sake you can imagine. So in order to generate sync and in order to generate all these signals, this is quite complex, whereas in VHDL, which is the programming language that you can use to program FPGAs, it's very simple to create things like counters, to create things like clock dividers here, and to quite easily extend them. So a lot of the things we see here, these are inverters. This is going to use multiple chips. There are a lot of inverters in this design, and a lot of XOR gates as well. That's these things here. But when you're creating things inside of an FPGA, when you're creating digital logic inside of an FPGA, things like inverters, XOR gates, these very simple kind of primitives are very, very cheap. You can have hundreds and hundreds of thousands of them, and it's literally, a line of code that can generate, 10, 20, 30, 40, however many you want. And so that combined with, and let me scroll down to the image of the patch bay, that combined with this absolutely enormous patch bay, I think it's like 64 by 62. Come here, where are you? Here we go. Nope, that's not it. This is it. Sorry, it's 58 by 54. This enormous digital patch bay. Creating one of these, a physical one in real life, would cost you a fortune. It would cost you so much. And in the original, this was split into 4, I believe. 4 kind of separate pin matrices and then wired together between them. It would be, it would just be outrageous. And it would make any kind of clone that used real chip hardware, individual discrete chips, just incredibly expensive and prone to all of the kind of problems that the originals have, in that you have so many signals and such a huge signal path, so many chips. It's just not practical to build that anymore. So the thought was, how can we build and give people access to a real hardware version, because that's what FPGA designed things are. They are hardware. How can we give people access to an EMS Specter? How can we let people play with an EMS Specter? Number one. And then number two is, how can we, once we've created, the EMS Specter, and it's in a little box and it's got an interface and you can use it and play it live and do all the stuff the original could do, how can we extend it? And this is something that I often, I've discussed this with Remy a fair bit. This is something that always kind of frustrates me when people clone or reproduce a kind of important piece of hardware, typically it's audio, like, you know, a 303 or something, they will clone the good things and they will clone the bad things. And that makes sense because you want the idiosyncrasies and the history, and you want the way of interacting with that instrument that created all of the fantastic music or art that came from that. But I think you're really selling yourself short if you don't also have an eye to what has changed and what has happened since in terms of interface design, computing power. So when you clone a 303, when you make a new 303, it's great that you've got that hard as hell programming interface, because people who know the original know it. They know how to use it. They'll be nice and fast with it. Brilliant. But for people who haven't used it, it's an unnecessarily high barrier to entry. And since there are only 14 of these, very few people have used them. So I want it to be possible for people to use it as it was originally intended. The massive matrix, all this stuff, the way that you route signals around. With an eye, though, and this is much more Remy's domain as an industrial designer, much more with an eye towards, yes, but is it possible? Can we also have a mode of interacting with it that is much more aimed at a contemporary user, at a contemporary audience, something that feels more natural, something that has all these features, but a flow that makes more sense and a flow that is easier to use, easier to perform with. We have this massive pin matrix. Trying to perform by dropping pins in and out, not easy at all. And the analog side, much better. We have some faders, we have some sliders. There's an external video input. If you want to know more about what actually goes in and out of this, what the interface was, please, I suggest, do yourself a bit of Googling for all the kind of history and that kind of stuff. But maybe it's worth, I've talked about FPGAs a lot. I said that word a lot, but I never clarified what that meant. So FPGAs, field programmable gate arrays, are for me, they're a really kind of magic device. So if you think about a normal microcontroller, you think about your Arduinos and you think about your ARM cores and ESP32s, all these things, your parallax propellers, they all they have a CPU, memory, all that kind of stuff. They execute the code that you write line by line. So, you program it in C or embedded Rust or whatever, and line by line, it will execute your code. The difference with FPGAs, right, is that the code you write for them is not a list of instructions. And here's a simplified look here. The code you write describes the internal, this may be a better one, describes the internal architecture and how you would like it wired together. So inside of FPGAs, there's normally thousands and thousands of these little blocks. We've got memory, we've got DSP, so digital signal processing stuff, inputs, outputs, and these things, combinational logic blocks. Sometimes they're called LUTs. What they are able to do is represent logic, represent logical operations. And so the kind of theory behind FPGAs is that designing a digital system, something that previously would have lots of different chips and you'd wire them all together on a board and you'd, get different chips from different suppliers and you'd build a system and da-da-da-da-da-da-da-da. The idea is that you're able to achieve that inside of a single chip here, and that thus greatly reduces the cost. But it gets better because FPGAs are reprogrammable, hence field programmable, programmable in the field. So field programmable gate arrays are able to have their contents, so how they are organized, the code that you have written to pull them all together and route signals through them, you're able to put in a new design. Remove a design, put in a new design. And what's great about that is you can develop and add features, and it's a much smoother development process. You don't have to print new circuit boards. You don't have to, jump back into your CAD program and redesign your circuit, swap out some chips, and especially with video stuff, video ICs always go out of production, which is a pain in the ass. This gets around some of that. And so what is great is that pretty much anything you can think to create using logic, processors, video generators, embedded microcontrollers, memory interfaces, all these things you can create inside of these chips. And that's exactly what is happening. That's exactly what I'm doing here. If we jump to MVP1, so this is where the demo that I'm working on at the moment, which will eventually go on to a little Spartan 7 FPGA board, which is one of the cheap. It's the cheapest line from Xilinx, cheapest line of FPGAs from Xilinx at the moment. From the digital side, that's this stuff over here. A lot of work has already been done. I've already created a lot of these components so far, and it is 2nd of the 6th. It's the 2nd of the 6th. So what has been built so far is X counter, Y counter. Slow counter's about half built. Our overlay gates, our inverters, edge detector's about 50% done. Delay is done, flip-flops are done. Video input is done in terms of how it is working here. And our outputs, the EMS Specter uses YCRCB as its color space, which is a television color space with a pretty long history. And so far I've created something that will convert from that color space using these bits through to RGB so that we can display on a traditional screen. And looking through, we have a bunch of other kind of things done. Oh, and kind of most importantly is the matrix is done, the pin matrix. At the moment, it's possible to have, so these are all outputs. At the moment, it's possible to have 4 different pins per column here. And if we let's look at the original picture. We can see if we look at the original picture, it's pretty rare that you'd have that many going to a single output. But here's what's great. Because it's digital logic, because it's an FPGA, if we want, we can just add more. We can add more pins per column. Or less if you need less. And that's one of the things that's brilliant. And eventually there will be, software control. There will be a kind of hands-on control level to this. At the moment, because it's still in kind of coding land, which in a future video I'll kind of go through where it's at and how I'm doing that. So at the moment we're able to see these things, these simulated images that are coming out. And what's great about that is that it gives you a real kind of clarity of like what works, what doesn't work, what, as these modules are getting hooked up, as I'm inserting this stuff, you can actually see, you know, I say real time. For hardware, this is real time. You know, in a minute, in 2 minutes, you can see if what you've done works, if what you've done makes sense. And Remy was over here the other night, and we were hooking up inputs and outputs, you know, and seeing what came out. And even though that was a very slow, arduous process because of how we're doing it in code, and we have to build the simulation and then there's still like an amazing kind of spark moment where, you know, you hook up a counter to an inverter to an overlay gate and another counter, you know, to an edge detector, and then you combine them all, you know, on the Luma and Chroma outputs, and you see this image that looks like what you recognize, you know, what you recognize from the Spectron. And that's a really like kind of lovely feeling. So I just wanted to give a kind of brief overview of what we're doing, what the goal is, what the plan is going forward, and also say if you want to contribute, the ways that people can contribute at the moment is, hey, if you are, where'd you go? Oh yes, if you're an FPGA engineer, there aren't too many of those compared to other things. But if you're an FPGA engineer and for whatever reason you're also a video synth nerd and want to get involved, the information's here. Please hit me up. Alternatively, if you have a lot of money, but not the skills, and you want to help see this thing become real, which it's humming along at a very fast rate towards becoming real, we have a PayPal donation button. There'll be potentially more options in the future when it comes to circuit board design and when it comes to more of the getting a real hands-on thing kind of out into the world. But yes, it's this, and it's going to be, sorry. So yes, thank you for watching. If you've hung around this long, you obviously have, you know, a keen love of video synths and the EMS Specter, or possibly FPGAs. So take a look at the GitHub repo featured here. Take a look at all the resources. Maybe do a bit of Googling if you want to know more about the Spectre, the Spectron, MES in Melbourne, who have one. Currently, like I said, not functioning, but, you know, they have one of the 14 in the world. And if you would like to be involved and can be involved, hey, please hit me up. Be fantastic. Be fantastic to talk to people. Also, let me know if you have used one of these. Have you seen one of these? Have you used one of these? Do you rate it? What kind of experience do you have with this very kind of odd piece of video synthesizer history? So until next time, when I'll probably talk more about the actual development process and how that works and how that's going, stay cool.